Hello students. In this video we're going to prove this identity involving the gradient operator. So we have two scalar functions multiplied by one another, and we're going to take the gradient. And as you would suspect, it behaves just as the product rule in one dimension does. So you may remember when you take the derivative of a product of two functions, that's one function left alone times the derivative of the first function plus the first function left alone times the derivative of the second function. It works the same way. However, keep in mind that g is still a scalar function. However, the gradient of f is now a vector valued function. So there is a bit of a subtlety there. And similarly here we have a vector value function in g. So whenever you take the gradient of something, some function, some scalar function, you end up with a vector value function. All right, but let's just go through this verification now. So recall definition of the gradient of a scalar function. It's a vector where the first component is differentiated with respect to x, the second component is differentiated with respect to y, and if we had another dimension, it'd be differentiated with respect to z, and this can go on for n dimensions. Okay, so if we take the gradient of something, then it is that derivative of that something with respect to x in the first component, and the derivative of that something with respect to y in the second component. Now, in the first component, I just apply the good old product rule. So I take the derivative of the first function f, leave the second function g alone, plus the first function f multiplied by the derivative of g with respect to x, comma, and then I apply the product rule to the second component in a similar fashion. Now remember, when it comes to vectors, we have a sum of components here. So when I break this up, this plus sign is going to go in the middle. This will be the first component of the vector, and this will be the first component of the vector. This will be the second component of, I'm sorry, this will be the first component of the first vector, the second component of the first vector. This will be the first component of the second vector and the second component of the second vector. In other words, it's going to look like this. So you can just work backwards, and you can see that if I took g df dx plus f dg dx, I would have this first component. And similarly for the second component. Okay, not to belabor that point, we now have a scalar function g that I can factor out of the first summoned, and I have a scalar function f that I can factor out of the second summoned, and that leaves me with the gradient of f multiplied by g here in the first term plus f times the gradient of g, and that is what we wanted to verify. All right, good luck.